Hello friends, welcome to another case study example video of the application of our Lenz and Faraday's law, which is very important fundamental electromagnetic induction laws. Okay, hopefully you have already watched the introduction video of this chapter where we talk about magnetic flux, Faraday's law, and Lenz law. So make sure your foundation is right first before we enter into this realm. So if you look at the diagram before me, you will see that there's this blue rectangle thing, okay, shaded, to show you that this entire area consists of uniform magnetic flux density. So imagine that I set up some coils such that in between the coil there's an area where the magnetic flux density or the magnetic field is constant. All right, and what I'll do is I'll move this loop. Okay, so this coil, let's go label here. This is our friend, the coil. The coil is going to travel with constant speed forward. So constant velocity. So it's going to be able to maintain the speed v. Okay, so let's see first what happens between a position. Let's say I number the position, and this is position 1 to position 2. Okay, so if you think about position 1 to position 2, there is no change in flux. So since there's no change in flux, I can say that the induced EMF here would be 0. All right, all the way until this point. And I will show you later why. But at this part here, if you want to write an explanation, you could say that the flux change, or no flux change, so no induced EMF. This is essentially what we are drawing. Induced EMF against, whoops, you couldn't see the bottom one, so let me zoom out a bit. Induced EMF against the position of the coil. So at this part here, the first part that I draw, 1 to 2, there is no flux change, so there's no induced EMF. This is position 2. Okay, now what happens when the coil transition into the blue color area of uniform magnetic flux density? Well, let's see. Bring in table camera. Okay, so this is my table camera. All right, and you can see that in order to make this visual easier to understand, I'm going to make the diagram a little bit in place. Okay, so imagine that we have this coil from the outside, and then it's now going to enter in when it's touching here. When this edge is touching the magnetic field, if you look at the top here, this is the surface area, because once again, we'd like to remind you gently that the magnetic flux linkage here is equal to BA. All right, so right now at this position, there is no magnetic flux inside this coil, no area here, no blue shaded area. When will you have a blue shaded area? When the coil begin to transition in from no flux to flux increase. So when the coil is from here, 0 flux to increase flux, maximum flux. So when you transition from this position to this position, there's obviously a change from no flux to got flux. No flux to got flux. Okay, no magnetic field, B0, flux 0, to got magnetic field, flux is not 0. So whenever there's a change in flux, according to Faraday's law, there's an induced EMF. So what is the direction of this induced EMF? Well, think about it. The direction of this induced EMF must oppose this change. So what is the change that it is undergoing? It went from no field to this annoying cross field, and I don't want this cross field. So what do? I make a dot field. Okay, so I create a dot field. You can see there's a dot field here, and okay, there's a dot field here. This dot field is to oppose the increase in the cross field. But if you want to create this dot magnetic field, because what did Faraday say? Whenever you have a flux change, let's say from this position to this position, there's an increase in flux that is pointing in this direction, pointing into the paper. Okay, because this is cross. If we don't want this magnetic flux or this coil do not like this change, it will create its own dot flux to oppose this change, because it went from no flux and living its good life to got flux. So I don't like this increase, I make dot flux, or out of the plane of the paper to oppose the flux that is going into the plane of the paper. Okay, so once again, no flux to got flux. We want to oppose this increase in flux that is going into the paper. To oppose this increase, the coil will induce its own EMF to create a field in the opposite direction to oppose this increase. So it's time to take out your right hand grip rule. Okay, we will point our thumb outwards into the camera to find the direction of current flow to create this outward magnetic flux. So I'm going to coil my hand, and I find that my hand is quick, like this. So B is going up, the hand is turning counterclockwise. So this would be the direction of my current, going in this direction. Okay, so current will flow like this, counterclockwise. Okay, so this is to oppose the increase in the blue color magnetic field. So you can think about it this way. Current will flow like this to create this outward field to oppose the inward field's increase. So now we're going to draw it inside our graph. All right. Okay, so here you can see your graph again. And when we transition from position 2 to position 3, okay, and we have drawn the direction of the current was creating a field that is pointing out of the screen or out of the paper. So a thumb should point towards your face, fingers are curling counterclockwise. So from here to here, from here onwards the current will flow this way. Okay, and this creates a dot magnetic field. So this is your, I'll label this one for us. This is our induced current, and this dot field is to oppose change. We don't want this change to happen. So I'm going to zoom in a bit so you can see my writing. This current will flow in this way to oppose. Until this point, there will still be opposition. And this dot field is to oppose the change. So maybe you'll be thinking, okay let's take this direction. For a while, there will be current flow, and the current will flow like so. Go up, maximum here, come down, like a pulse. And you might be wondering, Miss, why is the EMF maximum here? Well, let's go back to the table camera and stare at the shape of the coil first. Okay, so if you look at the shape of the coil, you will notice that when it is at this position, this blue color area is very small. The increase is very small. Okay, I'm going to tear this off so you can see the coil again. This increase is very small until it begins to go here, and then the increase is the greatest in the middle. Okay, so although the speed is constant, but due to the shape of the coil, the change in area per unit time is the greatest in the middle. Okay, when the coil is right in the middle somewhere here. Here, your coil will experience the greatest increase in area. Because you see, let's say I move 1 cm. Oh, the area is so little. But if I'm here and I move 1 cm, the increase of area is actually quite big. Okay, imagine different strips. So at the middle here, the area will increase the fastest. Here, the increase slowest. And after that, the rate of change of area will decrease again. All right. So this is why you have that pulse shape in your drawing. Okay, now let's consider what happens after this completely enters. So you see, no current, no current, no current, no current, no current. Got current, got induced current, got induced current, got induced. Oops, no more induced current. You know why? Because now you have magnetic flux, but you don't have change in magnetic flux. So if there's no change in magnetic flux, this will continue 0, 0, 0, 0. Means got flux leh, got cut the flux there, don't care. Because it's not about cutting the flux. It's not about whether you have flux. It's about whether you change your flux. See the difference here? We are looking for change. Isn't that what the world needs? Some change. So from here, look at the area. It is, the flux is changing. It's full. Then it's constant. So until this point, the EMF induced, if I continue this graph, will very well be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Until this point where it is about to exit the field. Okay, now something interesting is going to happen now. This coil, although when it was moving from position 2 here to position 3 here, didn't like this magnetic flux, don't want. So it created that dot flux, now this dot flux, to say, no, I don't want this flux. I create this magnetic field because I want to fight you. I don't like you. I make this one to fight you. Okay, lor? So from no flux to got flux, you don't like, fight. Okay? But then after a while, the coil is like, hi, okay lah, fine lah. I will live with the fact that I have this inward pointing magnetic field or magnetic flux density. That's just the way of life, and everything is like, okay, wait a second. I like this inward flux, but you are taking away my inward flux. How dare you take away my inward flux? What do you think the coil will do? According to Faraday, the current will flow again. And once again, according to Faraday also, this current will induce the EMF to oppose the change. So previously the change was an increase. Now the change is a decrease from got flux to no flux. So if this change is a decrease, I am going to now induce a magnetic field that is a big cross, because I am like, hey, why you take away my magnetic field? Why? Why did you take my magnetic field away? I want the cross field back. Because we are opposing the change. From got flux to no flux, the coil don't like, so it will oppose the change by making this cross magnetic field. Ignore the dot. It is the cross magnetic field. Okay, it is cross. Right? So it will create this cross magnetic field to oppose the change. And what is the direction of current flow then? So now your thumb will be ready, not? Your thumb will point downwards. Downwards means your current will flip opposite direction, no? Clockwise. Okay? So that means your current will flow in clockwise motion. Okay? And that will look like this. Okay? It will flow clockwise. It's just going to flow like this, lor. Okay, how do you like my masking tape coil? Want to do teaching during lockdown? Okay, hopefully it's not too hard to see. The current will flow this way. Okay, sorry lah, this is all I have. Okay, I can't buy Sharpie during lockdown. Okay, so the current will flow like this. I don't have access to stationary shops. Life is hard, you know. Okay lah, not as hard as some people. Alright, so if you want to create this cross flux, why? To oppose the decrease. You see, this one is decreasing. So to oppose this decrease, and if I want to create the cross flux, I will have to make sure that this current will flow clockwise. Meaning the direction of current flow is flipped, you know. Previously it was counterclockwise, now it's clockwise, which makes sense, right? Because the coil is experiencing an opposite change. Previously, it was experiencing an increase on this side, which is great. So here at this part, the current flow counterclockwise. When it is exiting, the current will flow clockwise to oppose the change in flux. So this will allow current to flow in actually opposite direction. So just to honor my purple color, just gonna keep this here. We want to recreate this cross flux that was lost to us, so the current will flow in counterclockwise. So I'm going to draw opposite direction, right? So I will draw this one going down. Okay, so it would be, this one will go down the same amount, roughly try to keep it the same amount or same shape. Okay, not doing very well. Let me try to draw again. It should be the same shape, so it will be something like this. Okay, so this is how you will get your induced EMF. I'm going to bloop out the table camera so we can draw on the coil. Okay, so here, this one, as noticed, it will create a cross flux. Why? Because there's a decrease in cross flux. So now your thumb will point into the screen or into the paper, and your finger is, my camera is confused. Finger will turn clockwise. So it will turn clockwise like this, like this, like this, like this, like this. Okay, but after that, there is no more change in flux, so everything else is 0 till the bitter end. So you will get 2 induced EMF, and if you plot it right, the value of the induced EMF would be the same. Okay, so this means let's say this value here is E dot 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 dot. Let's say this value here is E. Then this value down here will be of the same magnitude, negative E. But there are a few conditions. So let us try to write down first what is happening at different portions of the graph, okay? In case we forget, who knows, things can happen to all of us. So at this point, what I'll say is from position 2 to position 3, the area of coil with the flux or with magnetic field increases. And because of this, the flux increases. So EMF induced. This is according to Faraday. If EMF is induced, what happens then? The direction of EMF, the direction of current flow. So this dot magnetic field is set up to oppose the change in flux, according to Lenz law. All right. So if that's the case, the second thing that will happen is that there has to be some opposition. Meaning to say you will have to experience some repulsion. Because if you think about this field, these two are in the opposite direction. So it's a bit like North Pole pointing North Pole. They will push. So this coil will experience a resistance. All right. So if that is the case, we actually need an external force to actually drag the coil in. So here to here, I'm just going to draw from here to here. An external force is needed to maintain constant velocity. All right. So I'll write this part here. Note 1. The external force is needed at both position 2 to 3. And let me finish labeling the positions first, okay? So this is 2, 3. I'm just going to call this 4, 5, and 6. So 4 is here, 5 is here, 6. So, and 4 to 5. 1, 2, 3, 4, 5, and 4 to 5. Because the induced current in the coil opposes the magnetic field, the uniform magnetic field. So if it opposes the uniform magnetic field, then what happens is that the coil will experience a repulsion towards, in the drawing is towards the left lah. That is one way to look at it, talk about force. Another option to talk about this, if let's say you don't want to talk about force, is conservation of energy. Or the external force is needed, okay, to do work to maintain, to do work, to maintain the kinetic energy of the coil. Then you might be thinking, if the KE is the same, then this external force do work to do what? The work done by this external force is converted to electrical energy. Because guys, energy don't come from nowhere. So although you induce EMF or the coil, this coil creates its own current, it is drawing that energy from the fact that your hand is dragging the coil in. Okay, so the work done by the external force is converted to electrical energy and eventually heat in the coil. So if you want to maintain the same kinetic energy, you need an external force. So I need an external force here. I also obviously will need an external force from here to here as well, until this point. Okay, here to here, all these places need external force. All right, so I'm going to just not label the V here. That's just not to confuse all of us. And draw the V upwards a bit. So it will maintain the same speed V throughout, if that is what we wanted lah. Okay, so the second caveat here is what happens. Okay, let's complete the explanation first, which I will write quickly for you. From 3 to 4, which is this position here, this flat part here, got flux but no flux change. Okay, so your induced EMF E is 0. Here also no flux, so no flux change, EMF 0. Okay, what about this part here? This part, okay, this part here, I'll use purple. This part, I will say that, okay, I'm just going to draw down here. I'll say that the area of coil basically is the opposite of the red one. Area of the coil with the magnetic flux density decreases because the coil is transitioning out. So the flux will decrease, and according to Faraday, decrease is a change. EMF or current is induced in coil. Don't worry, I will scroll up. Okay, so from here, what kind of magnetic field will we create? We will create a cross field to oppose the change in flux. Okay, so whether it is a cross field, I'm just going to draw this on black to remind you this is the coil, or the dot field, it depends on what is changing. If you increase, I don't like that you increase, I make dot to oppose. If you decrease, I don't like that you decrease, I make cross to recreate what was taken away from me. So the current will flip direction. Now, if there's no external force, what will happen here is that this peak will be less than E. Okay, so I'm just going to draw a smaller peak here for us. Okay, sorry for the lag there. So you will see that if there is no external force, what will happen is that the speed will slow down. So, I mean, this one will be a bit distorted. So here would be a bit lower. And then all of the graph will be lower. And then here will be even more lower. And then even lower some more. So this green graph here, if there is no external force. Because when you lose kinetic energy, let's say upon entry here, you already lose kinetic energy. So you are moving less fast, the rate of change is slower. So your induced EMF will be smaller already. So here already get the hit to be smaller, here will be even smaller. So this one is like this. Okay. In this case, right, so I'm just going to put another note here. For no external forces, the vertical line. So number 5. Without the external force, okay, the kinetic energy of the coil decreases for two reasons lah, because of the repulsion and also because the kinetic energy is converted to the electrical energy. Okay, so the coil moves slower, and because of this, your rate of change of magnetic flux or d flux dt is decreased. Move slower ma. So if d flux dt is decreased, the induced EMF is lesser, as decreases with time. All right, so that will be the final part in case they say, oh, there's no external force. What will happen? So the induced EMF will be smaller because the flux is moving slower. So the rate of change is slower. You throw the coil faster, then you get a larger EMF. Lor. Very instinctive one ma. It's about rate. So it's about how much you change and how quickly you change. But if let's say you're asked to calculate the EMF, okay, if let's say you need to calculate the value of this E, don't fret. We will go back to this BA. All right. So I think a final note that I will write here is, if we are to calculate E, okay, so here, to calculate, we can only calculate the average E. The E will be equal to change in flux over time taken. But the change in flux here will be change in BA over the time taken. Okay, B is constant, so it would be the change in area over time taken. So you need to know things like the dimensions of the coil and how quickly the coil is moving. Okay, so all of this we will probably cover in an example. So stay tuned for that. Okay, so this A here, in case you don't know. Oh, excuse the lag. Okay, this highlighted yellow A, okay now my computer is a bit laggy, so parts of the screen cannot see. But this highlighted A is the area of this coil. All right, the area of this coil. This be your A. Okay, so how quickly the area changes will depend on how fast the coil is moving. So if the coil is not moving at constant speed because there's no external force, kinetic energy is lost to electrical energy, so the coil will slow down, causing the EMF to drop because it is changing less. All right, so I think that's all. Go and think about ideas like this. I will turn around and record a unique example regarding this. What happens if there's no external force, and also how to calculate the external force on the induced EMF. But at least get the idea right first. From position 2 to 3, there's a change in flux because there's an increase in magnetic field density passing through the area of the coil from here to here. To oppose the change in flux, current will flow counterclockwise. Once the coil is fully inside the magnetic field, there's no change in flux. So there is zero induced EMF in the coil. When the coil is about to exit, there is a change in flux. Okay, so it's about to exit and there's a change in flux. This is a decrease in flux from here 4 to 5. So if 4 to 5 there's a decrease in flux, then the current will flow in the opposite direction to oppose the decrease. External force is needed to maintain the same speed. Otherwise, the coil will move slower because kinetic energy has to convert to electrical energy. And at the same time, there is a repulsion between the flux inside the coil and the flux of the magnetic field. Okay? And that repulsion actually slows it down. But it's easier to think in the perspective of conservation of energy. You are inducing current. Obviously, the energy has to come from somewhere. Either it's work done by external force to allow you to maintain the same kinetic energy, or kinetic energy is lost and converted to electrical energy. All right, so go try some examples. This is a very basic understanding of induced EMF, and how the idea of induced EMF is not as simple as you cut or don't cut the flux. It's not about cutting, it's about change. So in the previous example videos, you have seen how rotating a coil can change the magnetic flux. Changing the value of this B by adjusting the current can change the magnetic flux. In this case, now we're going to move some stuff. Previously, we moved a magnet bar inside a coil. Now we move the coil inside a uniform magnetic flux density. So all of this movement is just relative. Make sure you get your head on straight so then you know where the flux changed and you can analyze from there. Okay, lots of analysis for this magnetic induction chapter. I hope this finds you well. If you find this video helpful and useful, like and subscribe. Okay, share the video with your friends so we can all ace our A2 together during the pandemic at home. Take care. See you in the next one. Bye-bye.